Okay, let's start today's lectures. In the last lecture, I have give you the assignment to solve this problem. You have to solve the voltage and current in this network. And this is the current and the voltage across the inductor. So how can we implement this in the phasor system? We convert it into the phase voltage and convert the network into the phase impedance. So what is the value of omega here? Omega value is 10. Omega is 10 here. And the impedance of the inductor is L is equal to J omega L. L is equal to J omega L. Right? So the value of omega is 10 and the value of L is 0.2. So it will be 2J, right? And this will be written in the phasor form as 5 at the angle of 0 degree. And this will be 4 plus 2J. So that problem is very simple now. So look at the solution. So this is in fact is 4 plus J2 and the value of this is for sine is 5 at the angle of 0 degree and we convert it into cos. So it will be 5 at the angle of minus 90 degree. Minus 90 degree. So we convert this network into the phasor network, or we can also call this the frequency domain representation of the network, right? So this network is converted into J2 and the total impedance is 4 plus J2 and the signal, the input signal is 5 at the angle of minus 90. So how can we calculate the value of current? So for the value of current, we first calculate this impedance into the phasor form. And then we divide the voltage with the impedance and we will get this value is equal to 1.12 at the angle of minus 116.56 degree, right? So how can we calculate the voltage across the inductor? So we will calculate it by multiplying the phasor current with the inductor impedance, which is J omega L. So we multiply it by J2, which means that 2 at the angle of 90 degree. So by multiplying it, we calculate the voltage across the inductor. So we got these two values. One is the current in the network, and the second is the voltage across the inductor. So that's very simple. Now we convert it into the time domain representation. So first we convert the current into the time domain representation, and then we convert this into the time domain representation. So the value of current is in fact 1.12 sine 10t minus 26.56 degree. And the value of voltage across the inductor is 2.24 sine 10t plus 63.43 degree. So this is about RL circuit, and there are several uses of RL circuit. RL circuit can be used as a low pass filter and a high pass filter. And similarly, the RC circuit is also be used as a low pass filter and a high pass filter, right? So now we see the Kirchhoff law representation in frequency domain, and we calculate the overall impedance of the network. How can we calculate the overall impedance of the network? So for this, we use the Kirchhoff law. So Kirchhoff law is one for the voltage and one for the current. So in form of phasor representation or frequency representation, we have the sum of all the phasor voltages equal to 0, and the sum of all currents in the network is 0. So we will see this implementation in the network. So first we see the Kirchhoff voltage law. So the voltage applied in the circuit is the phasor voltage applied in the circuit is in fact divided into the n networks or n impedances. That drop is V1, V2, Vn, and the sum of all this is equal to the voltage applied. And you have seen this in first course as well. But here we are dealing with the phasor voltages. So we have V1, V2 plus up to Vn. And we can divide the impedances into Z1, Z2, Zn because it's a series network, and we multiply it by the current. So if we want to calculate the overall impedance of the network, so that is in fact is the V over I, which is in fact gives us the sum of all impedances in the network. And vice versa, if the voltage is known, So, and we have to calculate the current in the network. So we will first find the equivalent impedance of the network and divide it by the phasor voltage, and then we got the value of the current. So in this way, we will get the value of current in the network. So this is the implementation. If we have a series network, so we apply the voltage divider rule if we have the two impedances. So how can we apply the voltage divider rule? So we know that the value of current is V by Z equivalent. So this is in fact is the Z equivalent. So V1 is in fact, we know that the Z1 I and V2 is equal to Z2 I. So we substitute the value of I in this equation. We substitute the value of I here and we substitute the value of I here. So we will get the voltage across the first impedance and the voltage across the second impedance. So in this way, you can see that the voltage is divided. If we have to calculate the V1, so we multiply the current with the Z1, and if we have to calculate the voltage across Z2, so we multiplied the current with the Z2. And this is called the voltage divider rule, that the voltage is divided into V1 this and V2 this. So because as we say, the applied voltage is divided into V1 and V2. So this is the rule of KVL. Now we see the implementation of KCL. In KCL, we know that the current is divided and the sum of all currents in the network is 0. So the current is supplied to the network is divided into n branches. Right? And we see that these branches are parallel. So the first current I1, how can we calculate this current I1? Because the voltage across all parallel branches is same, which is V. Which is V, right? And this voltage appear across branch Z1 up to Zn. Right? And first we calculate the current in the first branch. So this is the current in the first branch is I1, which is V over Z1. So the current I2 is V over Z2, and the current IN is equal to V over Zn. So in equation, we see that V is common, and we take 1 over Z1 plus 1 over Z2 plus 1 over Zn is the equivalent resistance of the parallel network. So that is equal to 1 over Z equivalent. Or you know that 1 over Z1 is the admittance of the network. So that is Y1 and Y2. That is Y1, Y2 and Yn. So this 1 over Z
सर
equivalent admittance.
एडमिटेंस के बारे में एक बार तो
Admittance, we have discussed in previously that admittance is the reciprocal of the impedance. So we can take the admittance because it is easy to solve the parallel network with admittance. So if we take the admittance, so it is very easy to solve the network, right? So that is the reciprocal of the impedance. So we see that the Z equivalent of the two impedance network is given by the multiplication of Z1, Z2 and Z1 plus Z2. And you can see that if we have 1 over Z1 plus 1 over Z2, so we have take the value of Z1, Z2, and we will sum up Z1 plus Z2. And the reciprocal of this is the Z equivalent. So at the next step, we have the current multiply this equivalent impedance, which is the voltage across the network. So this will give us the voltage across the network. And if we get the value of I1 Z1, so it is also give us the voltage across the network. So you can see it here, and you can see it that is also equal to I2 Z2. So how can we calculate the value of I1 if we have IZ equivalent divided by Z1? So IZ equivalent here and here, IZ equivalent is divided by Z1, so we will get I1. So substituting the value of Z equivalent, so we will get the current divider rule. So this is the current divider rule, that I1 is equal to Z2 by Z1 plus Z2 into I. So similarly, you can calculate the current in the second branch. So this is in fact is the current divider rule. So it means here you have seen to memorize that if you have to calculate the current in the first branch, you multiply it by the second impedance. And if you have to multiply the current in the second branch, you multiply it with the impedance of the first branch, which is Z1. So this is the way to memorize it. So this is almost the same you have learned in first course, but here we are dealing with the phasor current and phasor voltages. So for phasor current and phasor voltages, so we have the same rules to follow. So now we have an RLC circuit. So first we study the frequency domain equivalent of this circuit, and then we find the steady state current I by the phasor method, and then we calculate it in the time domain representation. So for this network, the supply voltage is 750 cos 5000 t plus 30 degree. So here you know the 30 degree is the phase, and omega, the frequency of the network, is 5000, right? So when we represent it in the phasor form, so we write that 750 at the angle of 30 degree. Right? So that's the simple way to represent it in the phasor form. So for this R, so R is equal to R. R is equal to R in the frequency domain or in the time domain. So R remains R, and because that is the real part, that has no effect. And what about the representation of this XL? That is equal to j omega L. And XC is equal to what will be XC is equal to? XC is equal to minus J over omega C. Right? So it is J by omega C. So this is the way we, what will be the value of omega? Omega value is 5000, and we have the value of L is 32 into 10 raised to power minus 3 Henry. And in case of XC, we substitute the value of omega is equal to 5000, and the value of C is equal to 5 into 10 raised to power minus 6, because it is microfarad. So we see here that we calculate the value of j omega L by this formula, that is J160 ohm. And the value of this ZC or XC is in fact is minus J40 ohm. Now we simplify this network, that we have the voltage 750 at the angle of 30 degree, and we have 90 ohm, J160 ohm and J140 ohm. So this is in fact is the frequency domain equivalent circuit. That is the frequency domain equivalent circuit. So now we can easily calculate the current. First step is calculate the equivalent impedance. So the equivalent impedance is 90 plus J160 minus J140, right? So the equivalent impedance is 90 plus J60 minus J40, and we will get 90 plus J120, and that is equal to 150 at the angle of 53.13 degree, right? So how can we calculate the current? So we calculate the current by dividing this voltage, the supply voltage, and this with the equivalent impedance Z. So this V is 750 by 30 degree, and this impedance is 150 at the angle of 53.13 degree. So we will get the value of current is 5 at the angle of minus 23.13 degree. So this is the phasor representation of the current, and now we can represent it in the time domain. So we know that this value is written in the time domain form because the value of omega is known, and here we have the supply voltage in cosine form. So we have this in cosine form, and we have the value of this is 5. So we have 5 value here, and the value of angle phase is here. So this is the way you can calculate or find the values in the frequency domain, and then you can convert into the time domain again. So for this network, there is another problem. So first you try to calculate the equivalent impedance, or we can say the input impedance. If we look into the network from these points, so what will be the equivalent impedance of the network, and represent it in the phasor form. And to represent it in the phasor form, we need the value of 50 radians per second. So that is the value of omega. That is the value of omega. So now you know that xc is equal to minus j over omega c, and xl is equal to j omega l, and this resistance remains 3 and 8 in phasor form. So first convert it into the phasor form. So for ZC1, we have the value minus J10, and we have assigned the value minus J10. So this is converted into the phasor representation, right? And ZC2 we have converted into minus J2 ohm. And similarly, the 0.2 Henry is converted into J10, right? By using this formula, J omega L, and omega is 50 and the Henry is 0.2, and that is J10 ohm. So now this is one impedance which is in complex form, or this is another impedance which is in complex form, or we have the frequency domain representation. And this is in fact is the another representation of the impedance value. So we say that is equal to Z1, that is equal to Z1, that is equal to Z2, and that is equal to Z3. So we can have Z1 is minus J10 minus J10, and this is 3 minus J2. So this is Z2 is 3 minus J2 ohm. 3 minus J2 ohm. So what will be the value of Z3? 8 plus J10. So now we have this in the complex form. So from this complex form, we have the phase representation. So we can solve it. Because the division and multiplication, we can do it in polar form. So this is 10 minus 90 degree, 3.6 minus 33.69 degree, 12.8 at the angle of 51.34 degree. So we can solve it in the complex form, and then we take the equivalent impedance. So first we know that Z1 is in series with the parallel combination of Z2 and Z3, because these two branches, this Z2 and Z3, are in parallel at this point, and this point. So these are in parallel. So this Z1 is in series. So we can write it in this form, right? So we will write it in this form. The parallel is, first we multiply Z2 by Z3, and then we divide it by the sum of these two impedances. So we substitute the values. So after substituting these values, we will solve it, and we will get the answer, which is 3.2 minus J 11.6 ohm, right? So in that way, we can have the input, the equivalent impedance, or the input impedance of the network. So this is also called the input impedance of the network, because we are looking from the input side. We are looking from the input side. So this is the input impedance of the network. So everything is clear at this up till this point. Okay, so we move to another network. So in this part, we have to calculate the output voltage across the inductor, which is 5 Henry. And so let's try it for yourself. I will give you 5 minutes to solve it.
सर एक दफा जरा अपर स्लाइड पे कीजिएगा.
जी. This one. And then you calculate the so first thing is that you have to convert it into the phasor representation. So for phasor representation, you need to know the omega, the value of omega. Do you know the value of omega here? So the value of omega is 4. So that is omega. Right? So now calculate the XC and XL. So for this, you calculate XC, and for this you calculate XL. So the formula for XC is minus J by omega C, and the formula for XL is J omega L, right? So once you calculate, then you calculate the equivalent impedance of the circuit.
Yes, sir.
So the equivalent impedance is that XC and XL are in parallel. These are in parallel. These 2 points are in parallel. So you take it as the parallel impedance, and after solving it, you sum up into 60. Okay, let's move on and look at the solution. So 10 millifarad is converted into this J4 into 10 into 10 to the power minus 3. So which is equal to minus J25. That is equal to minus J25, right? So we substitute the value of Xc here, and the inductor value is 5 Henry. So this is J4 into 5. 4 is omega, right? And 5 is 5 Henry, right? And that is J20. So we put the value of J20 here. And this voltage 20 cos 40 minus 15 degree is 20 at the angle of minus 15 degree. Now this is the frequency domain representation or the phasor representation of the circuit. So now solve it. So first we solve the this Xc and Xf and sum up into this impedance. So we will see here that this parallel impedances is multiply and then sum up. So this is in fact is the equivalent of this is J100 ohm. So J100 ohm is sum up to Z1, which is 60 ohm. So 60 plus J100 is the equivalent impedance of the network. So we see here that we apply the voltage divider rule because it is the two impedances in series, and we have to find the voltage across the second impedance. First, I calculate the voltage across the second impedance because I need to calculate the voltage at these points, right? So that voltage is same across this point. So this is also V naught, V out. This is also V out. And that is also V out. From this to this is also V out. So if we have to, if we calculate the voltage across the second impedance, so that is same for the two branches, right? So that is same for the two branches. So this is in fact is the supply voltage Vs in phasor form, or we have this 20 at the angle of minus 15 degree, and this is J100, which is the Z2, and this is divided by Z equivalent. Because in series voltage divider network, because this Z1 and Z2 are in series and we are applying voltage divider rule. So if we have to find the voltage across Z2, so we multiply it by Z2. So the value of this output voltage will comes is 17.15 at the angle of 15.96 degree. So now we convert into time domain. So this is the time domain representation of the network. So is it clear? So I hope you have no question up till now, because that's very simple. And now we move on to a complex network where we deal with the delta to Y and Y to delta combination. So the derivation of this conversion you have learned in the first course, and here we just recall the formula for this conversion. So the formula for this conversion is we learned that we have the delta network, we have the delta network, and we have the Y network. This is in fact is the delta network and we have the Y network. Now we need frequent conversion from Y to delta. So first we see that how can we move this way? How can we move from this way, which is Y to delta? Y to delta. So Y to delta. So I just give you the hint to recall the formula, right? So this is in fact is the Y to delta. So Y to delta is that we have known the value of these three impedances, right, which is of delta network. ZC. And now we have to calculate the value of Z1, Z2, and Z3, right? So how can we do this? Z1 is in fact, this Z1 is in fact is the product of the two adjacent, right and left. So this is right and left, and we divide this by the sum of all three impedances, which is right, left, and bottom. So this is the way you have the value of this Z1. Right? So similarly, you will calculate the value of Z2 and Z3, right? And in Y2 delta, we have this, we have the reverse of this. We have these three values are known. Z1, Z2, and Z3. And first we calculate the value of ZA. First we calculate the value of ZA. So how can we calculate the value of ZA? So we do the product of all the three impedances 2 by 2. So we start multiplying. So it starts from Z1, right? So every time we will have Z1, Z2, Z2, Z3, and Z3, Z1. So we have this at the top, and we will divide with the opposite Z1. So the numerator will not change. It will remain same all the time. So we will divide with the opposite impedance. So this opposite impedance of ZB is Z3, and that is in fact ZC is equal to Z2, right? Okay, I explain this again. In delta to Y conversion, we are given ZA, ZB, and ZC, right? And we will multiply with the right, left impedances with the sum of all the impedances. So that is delta to Y conversion. And Y to delta conversion, we have the sum of all the impedances 2 by 2, and then we divide with the opposite impedance. So this is the Y to delta conversion. So it is up to you that you name the impedances in the network, because you name Z1, Z2, Z3, and you will name ZA, ZB, and ZC in the network. So it's up to you how you name it. So look here, that you name ZA in such a way that opposite is Z1, you name ZB in such a way that the opposite is, I might not sure that is ZB is Z. ZB is in fact is Z2 here, and ZC is equal to Z3 here. So we will try a problem and then it will be clear. So we have to find the current in a network in which we have delta network. This part is the delta network. This part is the delta network, right? So we solve this delta network first because it's already the phasor representation. So we don't need to convert it into the phasor representation. So let's move on and see that how we have this delta network. So ZAN is in fact is how we can have to convert this. We need to multiply these two impedances, right? So to find this value of ZAN, right? And then we sum up all the impedances. Sum up this, and sum up this, right? So ZAN, you calculate the value of ZAN and ZBN and ZCN. So after calculating this value, so you will put this value here. So this is the network that this is split up into the Y network, right? And now the problem is very simple. It is just same like we have do this problem. So it's the same problem as we do here, and it's the same problem we do here in this problem. So there are two parallel networks and one series network. So after converting this delta into Y, this delta into Y conversion, so we have this equal to Z2 and this equal to from this point to this point, this is equal to Z3, right? And this is in fact is equal to Z1. So this is Z1 plus Z2 parallel to Z3. So it's very simple. If we don't do this conversion, so we cannot have the solution of this problem, that we cannot find this impedance, we cannot find this impedance, and we cannot calculate if we don't find this impedance, so we cannot calculate what voltage at this point P. So that is unknown. So for this, if we have this point, make this point common, so we are able to split the networks in three impedances, which can be easily known. So in complex networks, we have to solve Y to delta conversion. So now it's very simple. So the next ahead problem is familiar to you. So you have this conversion and you can solve it, this equivalent impedance to this value 13.82 at the angle of 3.333 degree. So that value is plus and and that value is minus. So we just simply multiply the voltage with this known impedance to find the current in the network. So that is the phasor representation. So you can, because we have not given the input voltage in the time domain, so no need to calculate it in the time domain. So any question up till now?
No, sir.
So I will post an assignment for you to explore that what are the usage of RC, RL and RLC networks.
Okay.
What is the usage of these three type of networks? And once you know it, then we will discuss it in the lecture that how well you have done your work, and then we can discuss it in the lecture. So I will mark your attendance before you leave. And first I stop recording.